Hello, it is Mrs. Scarple again, and this is part 2 of lesson 6.4, Exponential Growth and Decay. In this part, we are going to focus on compound interest or compounded growth. So compound interest is the interest earned on the principal. Principal is the initial value, and on any previously earned interest. The balance y of an account earning compound interest is found with this formula. Y, which is the final amount, equals P, the initial amount, or the A in our exponential growth and decay functions. 1 plus R is that annual interest rate in decimal form over N, the number of times interest is compounded per year, raised to the NT power. Again, N is the number of times it's compounded per year, and T is still time. In this case, it's specifically the number of years. So what do I mean when I say the number of times interest is compounded each year? Well, if we say something is annually, that's only going to happen one time per year, or once per year. If I say semi-annually, it is going to be twice per year or 2 times per year. Quarterly is 4 times per year. Monthly is 12 times per year. And weekly is 52 times. So when you're having to determine what is N going to be, you're going to want to think of how often these items happen during a year. In our first example, we are going to be depositing $300 in a savings account that earns 3% annual interest, compounded monthly. Write a function that represents the balance after T years. So if we remind ourselves of what that function is, we have y equals P times 1 plus R over N to the NT. And let's just identify what the different parts are. P will be the $300. R is that 3% in its decimal form, so 0.03. N, because we're saying monthly, is going to be 12. And then T is time in years. So if we write a function for this, we're going to have y equals, y equals 300 times 1 plus 0.03 divided by 12 to the 12t power. And we could simplify that to y equals 300 1 plus, I just divided 0.03 by 12, and that decimal value is 0.00 25 to the 12t, and then we can simplify it further. 300 times 1.0025 to the 12t. Now, something I'd like to point out, this was happening monthly. If we have it compounded annually, our n values would be 1, and we would basically have an exponential growth function. So here we have a table that is showing the balance of a money market account over time. Write a function that represents the balance after t years. So as we can see, our time is just happening in years, and we're just looking at our balance. So we just need to use a regular growth equation. We don't need to use that compound equation. So here we're going to have the initial balance. Our A value is going to be 300. We are going to need to find that rate that it is increasing. So if I take and divide 312 by 300, so my 1 plus r is going to equal 312 divided by 300. I'm going to end up with 1.04 is the 1 plus r that will go in my equation, and then t for years. So we have y equals 300 times 1.04 to the t power. And I can take this table and I can graph my information. So if we have a balance of 300, so I'm going to put a break in my vertical, and I'm going to go by ones across my x-axis. So this is the years. And then the y-axis is the balance. And it looks like I could probably go by let's go by fives, but I am going to label every other one so it looks like I'm going by tens. So we start with 300, and then we have 312, then we have 324.48, so really close to 325, and then we have 337.46, and then we have 350.96, then we have 365. And we want this, if you look, this shouldn't all be increasing exactly the same. It should be a sort of curve, but it's probably a little hard to see that it's a curve. So now we're being asked to graph the function from part A and the function from example 5 in the same coordinate plane. So let's go back and look at example 5. We have 300 times 1.0025 to the 12t. So what I'm going to have to do is plug in my years for t and evaluate this. So we have when t is 1, so I'm just going to call this, well, actually let's start with year 0. We have that starting balance of 300. Then for year 1, we're going to have 300 times 1.0025 to the 12 times 1 power, which is going to be 12 times 1 is 12. That's going to be approximately 309.12. Year 2, we do the same thing. Only this time is going to be 12 times 2, or to the power of 24. $318.53. Year 3, we have 300 times 1.0025 to the 12 times 3, or 36th power. $328.22 approximately. Year 4, we're going to end up multiplying 12 to the 4th power, or the power of 48, and we have 338.20. And then year 5, we want to take 12 times 5, or the power of 60. And we have about 348.49. So if we plot these, we know we're starting at 300, and then it's 309, 318, 328, 338, and 348. So this one is growing too, just not quite as fast as the function where it is compounding annually at a rate of 4%. The value of a car is $15,000. It loses 10% of its value every year. Because this is every year, we can use an exponential decay function. So 15,000 will be the A. 10% is equal to 0.10, which will be the R value. So our function will be y equals 15,000 times 1 minus 0.1 to the t. And we can simplify this to y equals 15,000 times 0.9 to the t. Find the approximate monthly percent decrease in value. So if we want to find the approximate monthly decrease in value, we're going to need to do a little bit of extra work on our rate here. To find that value, we know we need, for monthly, it's 12 times in a year, but this is being calculated annually. So we want to take this and rewrite it as y equals I'm going to type this. I think my computer just changed some things on me here. So I'll type it in purple. We're going to have y equals 15,000 times 0.9, and what we're going to calculate is 1/12 of 12t. 1/12 times 12 equals 1 year. But we're doing things, we want to find out that approximate monthly percent decrease, so we need to find what 1/12 of that is. So using our properties of exponents, we can actually use 15,000 times 0.9 to the 1/12 power to the 12t power. So then when we're looking for that decrease, we need to find what the decay rate is. So we're going to do 15,000. We're going to actually calculate that 0.9 to the 1/12 power. And again, when you're putting that in as an exponent, you can type it as 1 divided by 12. And we have approximately 0.99. To the 12t power. So for 1 month, if we want to find what that decay rate is, we're going to do 1 minus r, change my color here, 1 minus r is going to equal 0.99. So we're going to end up with negative r, because I'm going to subtract the 1 from each side. So negative r is going to equal negative 0.01. So r equals 0.01, or a 1% monthly decrease. So we need to graph the function from part A and use the graph to estimate the value of the car after 6 years. So if I use the function from part A, I'm just going to be plugging in for t, just like I did on the previous example. I'm just not going to write them all out on here. I'm going to be plugging in for t our time. Oops, I want this in purple. So we have 0, 1, 2, 3, 4, 5, 6, and then we have, actually, I'm going to, well, yeah, we'll just go ahead and graph it. So when I put 0 in for t, this 0.9 is going to be to the 1. So we're going to have 15,000. And since we have 15,000, I'm going to put 15,000 up here. As our starting value. And I might as well just give us the numbers. So after year 1, it's going to be worth 15,000 times 0.9, $13,500. Year 2, it's going to be 0.9 to the 2. So that's 12,150. Year 3, that's going to be 0.9 to the 3. $10,935. Year 4, .9 to the 4, 9841.5. Year 5, is 8,857.35, and then we have year 6, is at 7,971.62. So when I put my values on my graph here, I'm going to go, each one of these is going to be 1,000. So 13,000, 11,000, 9,000, 7,000. Let's adjust this just a little. 13, 11. 15, 14, 13. And I'm going to put a break in here. So we know we start at 15,000, or yeah, we start at 15,000, then we're at 13,500, and then we're at 12,150. and then we're at 10,935, then we're at 9,841, then we're at 8,857, and then we're at 7,800, oops, went too far. The way this example was written, we should have made an estimate using a calculator, graphing the function on the calculator and making the estimation. But we can see what is happening here. And if we have a function, there's no reason to use a graph to make an estimation. So again, across the bottom is time, across the side is the value of the car. And this concludes exponential growth and decay.